So in this video we will attempt to look at the methods of preparation of alkenes. And to understand this topic, first of all you need to have a basic idea of what alkenes, alkenes and alkynes are, which is expected of you. Method number 1 is preparation of alkenes from unsaturated hydrocarbons, and unsaturated hydrocarbons are alkanes and alkenes. Alkenes and alkynes. So this is very simple, and I'll illustrate the same with an example. Two examples to be precise. Let's say you have ethene, CH2 double bond CH2. All you have to do is you have to break one of these bonds, the second bond, by adding hydrogen in the presence of nickel or platinum to form CH3. So we had ethene and we precisely made ethane. We must note that in this reaction the catalyst is nickel or platinum. It could also be palladium, and the rates of the reaction depend on the catalyst, but the catalyst does not take part in the reaction itself. We could look at a very similar example again, that is, if you had maybe CH triple bond CH, ethyne, and you had to add two molecules of hydrogen and also nickel or platinum or palladium, whatever suits, you would still end up with CH3CH3, that is ethane. The mechanism is very simple. This pi bond is broken, and instead of that the carbon attaches one hydrogen to this part and one hydrogen to this part. Now the next, one thing to note is that you cannot prepare methane by this method, because for methane there is no corresponding alkene or alkyne, so CH4 cannot be made through unsaturated hydrocarbons. This process is also called hydrogenation. Very simple, just adding hydrogen, breaking the pi bonds. Now moving on to the second type of method of preparation of an alkene from alkyl halides. Now this method has many subheadings, and we will start with Wirt's reaction that states that when an alkyl halide is treated with metallic sodium in dry ethereal solution, a symmetrical alkene containing twice the number of carbon atoms present in the alkyl group is formed. What does this mean? Let's take an example. This is Wurtz reaction. So an alkyl halide is something like an alkyl group attached to an halogen, right? And what exactly happens in this kind of a reaction is you take two of these alkyl halides. For example, it could be CH3Br, CH3Br and CH3Br. Now we take an alkyl halide and we treat it with metallic sodium. So we need to take some sodium as well. It's pretty obvious that their reaction will occur in dry ethereal solution. We just write it as dry ether. Now it says that when such an arrangement is made, a symmetrical alkene containing twice the number of carbon atoms present in the alkyl group is obtained. Simply speaking, you have Rx here, you have Rx here. The alkane will be RR and you get 2NAX. In this case we had bromine and the group was CH3, so all we would get is CH3 plus 2NABr. Now it is very crucial to note that if you add, so the formation, what do you mean by a symmetrical alkene? If you see that when you add any number, any two numbers, whether it be any two same numbers, whether it be even plus even or odd plus odd, it will always give you an even number. So no matter what you do, the end product of this reaction will always give you an even number of products, even number of carbon atoms on the product alkene, right? Suppose we take another example, CH3CH2 Br plus 2Na plus CH3CH2 Br dry ether. We get CH3 CH2 CH2 CH3 plus 2 NaBr. Now we must note a few other things here. Firstly, this alkane group that you take, the halide group that you take, it should be either bromide or iodide. Because if you notice, fluorine, chlorine, bromine, iodine, in this particular case, fluorine would react way too violently, and to some extent chlorine would react very violently as well. To get a civilized reaction to some extent, we would need bromide or iodide. So keeping that in mind, Wurtz's reaction is carried out. Now we need to consider another special kind of variation of this Wurtz reactions. Suppose reacting alkyl halides are different, then a mixture of all types or variations of alkenes are obtained. Let's take an example, maybe CH3CH2I plus 2Na plus CH3I. So what we are doing here is we take this mixture with CH3CH2I. This is a ethyl iodide, right? And here we take methyl iodide. In such a case, this would react and it would give you CH3CH2 CH3 plus 2NaI. But there's a catch here. The catch being, this reaction surely would take place and give you an unsymmetrical alkene, but it would also react in this manner. Giving you this. And also methyl iodide would react among itself to give you this. So we get all possible products, one with ethyl iodide and methyl iodide, one with ethyl and ethyl iodide, and the other one with methyl and methyl iodide. Therefore, okay, all of these are in presence of diether. Therefore, it is crucial to note that even if Wurtz's reaction could produce unsymmetrical alkenes with odd number of carbon atoms, it is not very suitable for preparation of such alkenes because there would be dismixture and it would be very difficult to separate such a mixture from its constituents. So we now need a method that would help us to prepare our desired carbon atom having alkene. Therefore, you'll note that the next reaction we are done with words, so we are going to proceed to Curie-House reaction, which solves exactly our problem. Okay, let me take the sink now. Curie-House reaction. So is A. Yeah. So in Curie-House reaction, the alkyl halide is first treated with lithium metal in dry ether. So we take lithium metal here, that is crucial to note, and the resultant product is an alkyl lithium is treated with cuprous iodide to form lithium dialkyl copper. Finally, the lithium dialkyl copper is made to react with a suitable alkyl halide to obtain the desired alkene. Okay, so we can see that there is 3 steps to the formation of an alkane using the Corey-House reaction. So let's start with, it is always safe to take an alkyl halide that has bromine. So CH3 CH2 Br, and see, the alkyl halide is first treated with lithium metal in dry ether. So we take lithium metal in dry ether to get CH3 CH2 Li. That is the alkyl lithium, and the byproduct. Now we take this we take the product CH3 CH2 Li plus. Now this alkyl lithium is treated with cuprous iodide, so that is CuI, and it forms lithium dialkyl copper. So it forms CH3 CH2. This is dialkyl lithium copper thing, and then you have the byproduct again, that is lithium iodide. Balancing, we get this. Now the lithium dialkyl copper is made to react with a suitable alkyl halide. Now what does this suitable alkyl halide refer to? First let's take this CH2 twice CuLi. Suitable alkyl halide refers to, maybe you want a pentane. In that case, we already have 2 carbon atoms here. So if you want a pentane that is having 5 carbon atoms, you need to take CH3 CH2 CH2 Br. So you would have 5 as your product, right? Again, this is also reacted in the presence of diether, and our products are simply CH3 CH2 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 1 2 3 4 H3. This is our alkane, the N-pentane that we desired. Then ethyl copper next. So 1 2 3 4 5, and what's left is 1 2 and the copper. So CH3 CH2 copper, and lastly Li and Br. It is crucial to note that if we were to make, say, a heptane, then we would have to take a 5 carbon alkyl halide in this part. It's completely up to our discretion as to what we want to make as the final product, noting that we can get both odd and even products or alkenes. So to recapitulate what we have done till now, we saw how addition of hydrogen, simply hydrogen, and breaking the pi bonds in an alkene or alkyne will give you an alkene, and that methane cannot be prepared by this method because there is no corresponding alkene or alkyne. Then we moved on to the Wurtz reaction, which stated that an alkyl halide, when treated with metallic sodium in dry ethereal solution, will give a symmetrical alkene containing twice the number of carbon atoms present in the original alkyl group. So we could see how that procedure would work very easily, and that it is not very suitable to produce unsymmetrical halides with an odd number of carbon atoms. Therefore, we had to resort to the Corey-Hauser reaction, which would help us get any number of carbon atom alkenes that we would like to have. Moving on, we go to something not that important or common, but it's by the reduction of alkyl halides. What we do in this case is, again, we take bromides or iodides as alkyl halides, we reduce them. Okay, so reduction of alkyl halides by reducing them with red phosphorus and hydroiodic acid. Now, let us take a very simple hydrocarbon, that is maybe CH3 CH2 Br, and we react that with hydroiodic acid. We get CH3 CH3 plus HBr plus I2. Now the red phosphorus removes iodine formed in the reaction. Therefore, what the phosphorus does essentially is converts the iodine gas into this. And alkyl halides can also be reduced by hydrogen in the presence of a catalyst like platinum or palladium. Something like hydrogenation platinum or palladium. So we get an idea of the preparation of alkenes with the help of alkyl halides. And lastly, from alkyl halides, we also could prepare alkenes using Grignard reagents. Let's first look at what Grignard reagents are. The form of a Grignard reagent is RMgX. To state it simply, there's a magnesium attached to the halide as well as the alkyl groups, and they are very highly reactive and very extensively used in the synthesis of various organic compounds. So let's say we had our alkyl halide from before and some magnesium somewhere sitting around the room, and maybe even a dry ethereal solution. The resultant would simply be our MgX. An example of this could be maybe something like CH3 CH2Br plus Mg, giving you CH3 CH2 MgBr. Now we need to note the exact procedure as to how Grignard reagents would form an alkene. So we take this RMgX compound, and the CMg bond here, the carbon Mg bond, is very polar, because the carbon atom attached to magnesium is more electronegative than magnesium. As in the periodic table you would notice, magnesium is quite far away from carbon towards the left. So magnesium is more electropositive, carbon is more electronegative. Therefore, when a Grignard reagent is treated with water, alcohol, acid, or any proton donor, the alkyl group combines with the proton to give an alkene. Then water, again, it's a polar compound. There's an H plus and H minus. These are delta positive, delta negative charges. And what happens as a result of this is this R and this H positive end up forming RH, and we are left with this byproduct. For example, maybe you could take CH3 CH2 MgBr, and simply we could then write that this hydrogen would of course come to there, and then we would be left with MgOH. Yeah. The name of this compound would be hydroxy magnesium bromide. Therefore, we have now finally completed our second half, our first half and second part of preparation of alkenes using both unsaturated hydrocarbons and alkyl halides. In the next session, we will look into the preparation of alkenes using carboxylic acids, and of course from alcohols, aldehydes and ketones. Before that though, we would need to keep a few things in our mind. That being, these methods of preparation have various scientists who contributed to their discovery in some sense. Some even were awarded the Nobel Prize in Chemistry for their work. And it is crucial to note that fluorine, okay, so the halides are fluorine, chlorine, bromine, iodine. Writing this again, that fluorine is very violently reactive, and oftentimes iodine is very slowly reactive. But it's always safe to choose bromine, it's just that sweet spot. Also, it is crucial to note that preparation of alkyl halides by the Cody-House reaction, this part the dialkyl lithium copper part, you could also write the same thing as LiCH3 CH2Cu. Of course, that wouldn't make a difference. Some textbooks have that, and the mechanisms of these reactions are not very complicated and self-explanatory to the most extent. This is where I end my first video. Thank you for watching.